and then we can start class. Okay. Let's see. People who I didn't check at midnight or something. Last night, midnight was last day to take the makeup, I believe. Everybody who was going to do that, unless you have some other things you haven't told me about yet, or I didn't see an email this morning, I assume that the retake has been done. Okay, what about the other test? We have another test that's due Wednesday night, we said, right? Okay, I just got to keep the two classes. What I got to do is stop my mind on one class and go to the other class. I think that's where we are right now. Okay. Now we are in, some of us are in chapter 10. And I want to talk about a couple of things there. Actually, there's one thing I want to do before we get to that, and that was, and I'm going to look it up quickly because that's maybe the quickest way to do it right now with my blue fingers. See if it's in the index. Yes, on page 596, there is an interesting problem, I think. It's problem 27. And this is back in chapter 8. It is called Gabriel's horn. It's a problem. And I'm going to write the problem down real quickly, hopefully. If we talk about a set of points where,
Dr. Brady,
yeah,
there are people waiting to do that.
okay, I don't care.
Also, we need to check it, make sure we're recording.
We are, thank you. Okay, now that's one people. I don't know if anybody else out there. Okay, I don't see anybody else waiting. Okay, thank you. Okay, so y is between 0 and 1 over x. Okay, and so we want to take this region from 1, and x is bigger than or equal to 1. So if we work this out, we get this kind of a shape. And what we want to do is revolve this shape around the x-axis so that you get, in a sense, something that sort of looks like a horn. Okay? Now, what is the area of, what's the volume of this region? Remember that what we did there is we took pi times f of x squared and we integrated it from whatever we were doing. And so now what I want to do is put infinity up here, which is new. But if we let this region go forever, we could look at this improper integral, and I can take the pi out, and the f of x is 1 over x, so I get 1 over x squared, and from 1 to infinity, and presumably, because you're taking tests in it, you remember that when we have an improper integral, we allow ourselves to integrate something from 1 to like t. And when I do that, I will get minus 1 over t to, I need to put in, 1 over x, I need to put in 1 and t. And when I do that, I will get 1 minus 1 over t, which I take the limit of as t goes to infinity times pi, and I will get the answer pi. So if we are believing that the volume of this horn inside is okay to consider all the way to infinity, we get pi. If I would cut off the horn any place, I will get a number less than pi. The point is that we have an object that has a finite volume. Okay? Whether we consider it infinite in length or finite in length, it's a number less than or equal to pi. Okay, Now, what else do you have in this chapter 8? This is a little bit of review, which is one of the reasons why you guys are taking tests. I wanted to review this because it helps us remember stuff. Okay. What is the surface area of such a thing? And if you remember, that's 2 pi f of x integral and 1 plus f prime of x squared. So maybe you haven't done that as an improper integral, but that's what the surface area would be if I take the formula and instead of stopping it someplace, I let it go. Okay. So now, when I work that out, this is a little bit harder to integrate because you are doing 1 to infinity, which we'll play with in a minute. That's 1 over x and 1 plus f prime. F prime, when you do 1 over x, is minus 1 over x squared. And so the derivative is minus 1 over x squared, which I square. And so I have to try to integrate this. I'm not ready to do the improper part yet. I'm just trying to figure out what the integrand is right now. And if I make a common denominator of this stuff, I'll get x squared plus 1 over x4. And if I take the x4 out of the square root, I'll have x squared. Okay. And so what do I end up integrating? And is that right so far? If you differentiate 1 over x, you get minus 1 over x squared. If you integrate that, you get this. And so anyway, you get x squared out here. I'll get x cubed evidently. Plus 1 dx 2 pi. Okay. Now, if I've done that correctly, the integrand, that's going to be a trigonometric substitution of some kind to try to integrate this. And it's going to be a little bit nasty, okay, because we've got a lot of x's and stuff in there, right? Anyway, I want you to do that if you want. This is problem 27. When you do this, again, you want to find an antiderivative. Then you want to take a limit. So what you do here is actually do an antiderivative from 1 to t, just like we did over here. But what you're going to find out when you do that, you get infinity. Okay. Now, so what? This is a thing that has a finite volume and an infinite surface area, which is kind of an interesting idea.
Wouldn't that make it pi then?
I'm
Because
sorry?
wouldn't that be the same thing as pi? Because
When you integrate this, you will get a thing that will go to infinity. It does not exist.
okay, but it has an
That's why I
infinite
want you to do it, okay? Yes,
I'm sorry, I'm still working on the simplification from the second line to
from here.
from the second line.
Oh, this one?
Now on the left side of the board, from the second line
This
to
one?
the third line.
This one?
Yes, I'm still working on that simplification.
Oh, it should be x4. Whatever. Right? Yeah, thank you. I knew something was wrong with it, but I didn't know what. That's why I was looking back over it. This should be x4. Because when I do this, it's 1 over x4. So you make x4 plus 1 over x4. Okay, now, you're happy? Anybody else unhappy? Mr. Lammers, did you understand? The point is when you do the integral, if you have to do it correctly, when you do the integral, you'll get infinity. And I just want to point out that people who first did this were surprised to have a thing that you could fill up, but the surface area is infinite.
okay, I think that makes sense. This kind of reminds me of pi since it has a set value, but it has an infinite set value.
finite volume, infinite surface area. So this is one of the things that happens when you start considering infinity. And the people who did this did not have the real numbers yet defined. They didn't know what to do, so some of them made it religious, and they called it Gabriel's horn. Gabriel is an angel in Christian stuff in the Bible. And so it had to be an infinite horn in some sense, because it doesn't make sense as a finite horn. Okay, so it's just you will find when you look through stuff that was done in the 19th, 18th centuries, that sometimes things are given interesting names because people didn't know what to do with something they didn't quite understand. And sometimes whether facetiously or seriously, a religious name would be given because it was like a paradox or something to understand or something you take on faith. Okay. And so if the proper or improper intervals make sense, then we have to take on faith as you can have something with a finite volume and an infinite surface area. Well, they didn't understand how that would work, so they just have to believe it, you see. And I don't necessarily mean it's an organized religion. I'm trying to tell you why it's named Gabriel's horn. Okay? No opinions about religion, pro or con. I'm just showing you history here. Okay? And there's another thing that comes up in our stuff. That one of the ways people solve stuff was to try to model what a deity would do if the deity had the same problem. In other words, if you had to create something, you would do it most efficiently because you're the deity. Okay? You wouldn't wouldn't waste energy, time, effort, whatever, because you're the deity and you know how to do these things. So to solve some problems that come up in nature, the idea is to look for the solution which would be most efficient. And when the people went that direction, they actually found they found answers that satisfied every critical thought they had about the object they were trying to understand. And if you have something that satisfies every question you have about it, you believe it. And so sometimes there's a principle of least action, for example. There's a mini-max principle, something that minimizes the maximum of something. And there's all kinds of principles that are based on the idea that if you were going to do this and you had infinite power and infinite knowledge and infinite whatever, you would do things in a certain way. And so if you emulate that, maybe you can find the answer. Now, that also preassumes that there is an answer. You see, people seek the truth, assuming there is a truth to seek. So that's another thing, is there's a certain belief that maybe things have already been done by a deity, and therefore we need to figure out how it happened. If it was just chance, then that way of trying to approach the problem might not work. Okay, but if there's purpose in it, then you have to find the purpose. They're kind of, so this is how people thought, maybe still think, maybe that's the way I think, maybe not. I'm not trying to take opinions here. I'm trying to tell you something that's been going on in history. And a lot of times when people do things like burn witches and stuff, it's because they don't understand something. And so the easiest thing to do when you don't understand it is get rid of it. Otherwise, you might fear it. Okay? And to get off the subject here, for example, the first people from outside the island of New Guinea in 1926, just maybe this will interest you, maybe not. I'm full of such worthless bits of information. In 1926, the first airplane, there was an airplane that could fly high enough to get over the mountains on the boundary of the island of New Guinea. Up to that time, they couldn't fly that high. So as soon as they could fly over, they were surprised to find out that New Guinea was populated by people which they didn't know before. Actually, there's 720 tribes in the interior of New Guinea, which they didn't know about till they flew over the mountains to get into the inside. And the plane landed, I believe it was 3 people. They landed. Of course, the natives in where they landed had never seen an airplane before and didn't understand about anybody getting out of this thing. And they believed they were gods. Okay? Which we might believe too if somebody lands and they look different than we've ever seen anything, and so forth. Anyway, we call them aliens today, but anyway, they thought they were gods. And this particular tribe was not necessarily friendly, except they thought that the people who landed were gods, and therefore you better be friendly to the gods because they might do something to you. Until one of the people who got off the plane needed to use a restroom. And that's when the chief decided that they're not gods, because gods wouldn't have to find a place like the rest of us have to occasionally, if you understand. And so that's when things started to get a little bit belligerent. And so one of the men in the party shot a pig. And in New Guinea, pigs are very valuable. But they shot a pig to show that they had some power. And so the tribe became very friendly because they realized that although these are human beings, they are a lot stronger than they were. And that was the first encounter of outside people into New Guinea. Don't know if that interests you or not. But by the way, the 720 tribes have 720 different languages, and they're not compatible. And therefore, they've been warring for the last 2,000, 10,000, or whatever years, because these tribes all, and there's all kinds of interesting history I could tell you about. It's an interesting place to go. Well, I don't want to tell you about how I helped them in the warfare, but that's, I did something and it turns out that they liked it, and so they're going to use it in the next war. And it's very much like, well, I'm wasting your time. If you've never fished for certain kinds of fish that are very, they like to bite things, you know what kind of fish I might be talking about? In the South America waters, you have certain very carnivorous fish. Anybody know the name?
Piranha.
Piranhas, yeah. There are several kinds of piranhas. But anyway, you can fish for piranhas. And so once upon a time, I was fishing with some natives in the headwaters of the Amazon. And the problem is that they were bottom fishing. And the problem in the water is that water's got a lot of sticks and stuff on the bottom. They were constantly having problems with catching stuff. They had purchased hooks from somebody, so they had hooks, but they kept catching things. So I fashioned a bobber to hold the material off the bottom. And everybody in the village thought that was a great joke until I caught all the fish. And so now there's a village in that area that catches fish by using bobbers. Well, the problem is that I don't know whether I should have done that or not. You see, it changes the way it is. I didn't intentionally do that, but I thought, what the heck here? They'd never thought of it. Now they think about it. Anyway, enough wasted time here. But at least everybody in this class that I see is awake. Doesn't always happen. Okay, what's in chapter 10? The first section is mainly trying to introduce you to functions that we've talked about already last week or 2 weeks ago. We have a function and we have two functions of one variable that together, one of them tells you what x is and the other one tells you what y is, depending on some third thing called a parameter. And you don't graph the parameter, you're still doing things in the plane. And so for every t, normally we have like an interval, and the t might be time, but for each t, we get a point in the plane. And when you put together a whole bunch of t's, you get a whole bunch of points, and maybe you get a graph. Now, we don't graph the function, we graph the range of the function. We graph the points you get, we don't put the domain and range together. And since we get curves when we do this, one of the things you do is figure out what the length of the curve is. And you do the same thing. We talked about this last week, so I'm not going to redo all of that. But there's a formula for the length of a curve for things described this way. And that is to use the interval that you base the domain on. And you take the derivative of the x and the derivative of the y, you sum the squares. And if you remember, this is different than what we had before, which was if I have a function of x, now I'm going to call it g. If I have a function of x instead, so in other words, if I have a situation where I have an actual function of one variable, then the length of the curve is given by this formula. This is what you're having a test over. Okay. But if I describe it differently, parametrically, it turns out that you have this formula, and this one's much more general because it includes this one. This one includes this one when your x of t is just t, and your y of t is g of t. When you put these two things in this formula, you'll get this formula. Now, that's, I think, the third time I've said that, but that's what you have, and this is in section 2 of chapter 10. In section 1 of chapter 10, that's the arc length. Chapter 1 of section 10 is just playing around with these ideas and sticking various functions here and seeing what pictures you get. And when you do that, you quickly get very complicated pictures. And so what section 1 is mostly about is just familiarity. It's not, you can't do very much without a computer to graph stuff for you because stuff gets very difficult to graph by hand if you use very complicated functions. And now you get some interesting things happening too. And so I want to talk about something here. Suppose that x is the sine of t and y is the square of the sine of t. And t, let's say, is, I don't know, between 0 and let's say 4 pi. Now, this is one of these functions. If I call this function capital X, the book doesn't do that, but I like to do that. And I call the other one capital Y. I like to use capital X and Y for the function and little x and y for the variable you get. Okay, so what would the graph of this look like? So this is section 1. We play with plotting points. So if t is 0, then sine of t is 0 and sine square of t is 0. So I have plotted 1 point. That's exciting. Now, suppose t is pi over 2. If t is pi over 2, the sine of pi over 2 is 1. The sine of pi over 2 squared is 1. And so this particular thing goes through that point. What if t is pi over 4? Well, pi over 4, the sine of pi over 4 is 1 over the square root of 2, or if you like, half the square root of 2. And the square of that would be 1/2. So this square root of 2 is about 0.7, and this is about 0.5. And so what you get, if you plot points, is you get about 0.7 and about 0.5, and so you plot another point. And by taking various angles or various numbers, you can stick a number in and then square it. But after a while, you think, hey, wait a minute. If I would take y and substitute x, I get y as x squared. This is like going backwards. One of the reasons for doing these problems is because a function like this may not be complicated enough. Maybe we want to study things like this, except that's not a function. But we can study things like this using this idea. We can't study very well things like this using this idea. So we're kind of going backwards. We're trying to do the new thing, but actually we know more about this than we know about that. So what is it? A parabola. So now you got to be careful. You can't go too far here. So I draw a parabola. Hey, I got this graph, but I don't really. Why not? Why don't I get the whole parabola? And that's because the sine can never be bigger than 1, right? Sine of an angle is never bigger than 1. So the x can never be bigger than 1. So all this stuff up here doesn't exist because 1 is, this is as far as it goes. And the sine can't be less than -1. So what I've got is a graph like this. If I take y as x squared, I get a graph like this, but this isn't what I get at all. It's much more interesting. Namely, when I get to pi over 2, we said I'm at 1, 1. What happens when t is bigger than pi over 2 and less than pi? Well, the sine is still positive, but as the angle increases, the sine of pi is 0. So if I would put pi in here, I get 0, 0 again, I'm back here. So what happens here, if I start with t equals 0 and I let t increase, I climb up this parabola until I get here. And then as t gets bigger, I go back down. So I'm getting points more than once, even though I can't see them because they're on top of each other. And when I get past pi, I'm actually going to go this way because the x will now be negative. The y is still squared, so it's still positive. I'm still on the parabola. But what this does is gives me something that oscillates back and forth. So this new idea of parameterizing, having a function that goes into 2 dimensions with a 1-dimensional domain, can give us motion. So we can study motion along a curve as well as studying the points on the curve. And that's brand new. Okay, so this particular thing, if I stop it from 0 to 4 pi, it would start here, go up here once, gets up here to pi, comes back here by the time it gets to, goes up here to pi over 2, comes back here when it gets to pi, goes back here when it gets to 3 pi over 2, and back here when it gets to 2 pi. So what it does is it draws this once, draws it a second time, draws it once, and draws it a second time. If I would increase this bigger, it's going to go back and forth. So if I let this be r, real numbers, now the thing's going to go back and forth all the time. And that's a brand new idea. In fact, if we would change the curve a little bit, and, well, you know about a conchoid maybe, a cycloid. If I would take something like a wheel and put a light on it and drive around, and people see me go by, they would see some kind of a light would draw a picture. And if you did a time photography, you would see the light going along, and that's called, what's it called? It's called a cycloid. It is on page 800, 683. Okay? Now you might do that if you like to drive around town and scare people or something, because the people see this light going along. Okay? And if you really want to be excited, you know, you put lights in different places and make all kinds of stuff going along. And maybe in your neighborhood, this would be a big deal. I don't know. Okay. By the way, just question, do people still cruise around your age and wherever town you come from? When we first moved to Wichita, people were, at Friday nights, teenagers would cruise on not Main Street, but on either Central or Douglas. Take their car, driving back and forth all the time. Anybody?
It's not like, at least in my experience, I'll often take like the long way somewhere, but it's never just like driving to drive. It's like I'm going to somewhere, but I'm choosing to take like the scenic route.
You're just not driving up and down the street to show off or something.
No.
I think that's a lost art.
In college, we don't really have cars that can do that. No one
You
wants
know,
to see
people, as I say, when we first moved to Wichita, Friday night was crowded with cars driving up and down Douglas Street. Teenagers. And so on. Anyway, I think that's a lost art. Maybe you don't even know about that, right? That's interesting. Okay.
one of my parents.
Anyway, when you drive along here, this thing will make a picture. If you would turn this over, so turn one of these over, it's like a parabola, but turn one of these over. It turns out that if you would put something on here and let it roll down to here, if you use this shape, no matter where you start this thing, it takes the same amount of time to get to the bottom. When you start a little higher, it goes faster. It takes the same amount of time. Now, when that was realized, people decided they could manufacture clocks that did that, because this clock would be accurate, because however it swings, more or less, will always be the same. And so you can use something to generate a steady thing to turn your hands of your clock. And so that's one of the designs. And people like, who's the inventor that did everything back? I forget now, but anyway, I should know. Who's a very ingenious guy that built airplanes and all kinds of stuff 200 years ago. You know what I'm talking about?
The Wright brothers?
I'm sorry, no, before the Wright brothers.
Leonardo da Vinci.
I'm sorry, who?
Leonardo da Vinci.
Yeah, Da Vinci is, yes. Anyway, okay, so the point is that once they realized there was something that could use like a pendulum that would be not changed depending on how much it swung, that decides to design something called a clock. Okay, and so, for example, in my house, I have a clock called a flying pendulum clock designed by Da Vinci or somebody. It's one of the people, and it's an interesting clock. Only has one hand, because if you think about it, you don't need two hands, but that's another problem. If I have a clock, and this is 1 o'clock, and the hand is like here, and this is 2 o'clock, you know what time it is, roughly. Right? You guys don't care what time it is when you sit in here. You care how many minutes it is before the end and things like that. But 10 o'clock, 12 after the hour and 13 after the hour is the same time to you guys. Okay, 10 till the hour and 10 after is different. It's like, oh, we still have another 20 minutes. Okay? But 16 after and 18 after is about the same. It's time I'm packing up, man. Okay. So clocks used to only have one hand because they didn't need two. This is a very interesting day, isn't it? Okay, so in the first section of chapter 10, they draw a lot of pictures, mainly drawing them for you, okay, to try to show you the kind of stuff you can get into. And then they do some families of parametric curves where they take some pretty simple things and they show you nice pictures. And again, there's not too much we can do with it. There's some interesting things to read about, as I said. That's the things about the thing I said about the cycloid and stuff, that's on page 684 and so on. And so that's more of an introductory section for which there's some exercises and things. And some of the exercises, by the way, is exercise 24 on page 686, and it'll be something like that in WebAssign, where they give you a bunch of pictures and they give you some formulas and they say which formula gives you which picture. And these are not easy necessarily. In other words, these equations, like some of them have wild formulas, but some of them have pretty easy formulas, but wild pictures. And you might not guess that some nice formula has such a wild picture. And so it's more meant to be more fun than agony to try to figure out which equations on this page 686 is going to give you which graph. Now, nobody's going to ask you to do that on a test or anything, okay? It's more familiarity with the idea than it is doing anything like problem 6. Okay? All right, so, but when we get to section 2, that's when we get to this kind of stuff. Okay? And I want to do something else because I think the book does a bad job of it, so I'm going to do something else. And that is, what we're doing now is we're defining 2 new functions. One I call x, that gives me the variable x. So that's right here, x equals x of t. And I might have a y function that gives me y. Okay, so I got 2 functions just sort of described by these arrows. This says x depends on t and y depends on t by some formula described by y and x. Now, what have we had before? What we've had before is a function y that depends on x. So I'm going to assume there is such a thing. Okay, like a while ago when I have sine t and sine t squared, we found out that y was x squared. There was a relationship between the 2 variables. Okay, so what we studied before is when you have a relationship between the x and the y. Now we don't. Now we have a relationship between x and t and y and t. But maybe there's a relationship here. So let's suppose there is for a minute. So y of t, I'm going to assume, is phi of x of t. So this just is basically saying that there's a relationship between them that connects them. Well, if that's the case, I'm going to differentiate. When I do that, I need the chain rule. I differentiate the outside, leave the inside alone, and so on. And now I'm going to make a condition. If x prime of t is not 0, then y prime of t over x prime of t equals phi prime of x of t, which is phi prime of x, little x. Now, what's going on here? Well, if you have a thing where this is the function phi now, okay? If I have a setup to have an x and a y functions on some AB, so that for every t, I get a point here. This would be x of t and y of t. But also at the same time, for every x, I get a y. That's what I'm saying here. When I draw this, I'm saying I have two ways to look at this curve. One as a pair of things, two functions, and the other as a function of x. And what this does is it compares the derivative of this function phi with the quotient of derivatives of the functions y and x. Now, so what? What is this? What's the derivative of a function if you have a graph? It's the slope, right? The derivative is the slope. So the slope of the graph can be obtained by dividing the derivatives of these two. I'm given two functions, x and y. I can differentiate x and I can differentiate y. If I find the quotient of the two, that will be the slope of the graph of the function if it is also a function of x and y. And I don't need to find that function if I find all the slopes. See, if I know what the graph is and I know what this gives me all the slopes, then I don't have to actually figure out what this extra function is. It exists, but I don't have to do it. On the other hand, we might have a situation like this. And in this case, I don't have such a thing, but in little pieces, I have such a thing. I have a function this way. I have a function over here. I have a function here. So I have some pieces where I have function. But I might have this description for every t. So when is this going to give me the slope of things on the curve? As long as the denominator is not zero. Now, what is it like when the denominator is zero? What if I have a curve and the denominator is zero? That's when you have a vertical line, right? So where are things going to mess up if I have, I'll draw it bigger. If I have a thing like this, where do you think this is not going to work? It's not going to work right here. It's not going to work here. It's not going to work here. It's not going to work here. Those would be where the x is not changing. See, if x prime is zero, then x is like a constant. And so that's where things might be going up and down, but they're not going over. What happens when the y prime is zero? That's when the derivative of a function that exists would be zero. That's when the thing is flat, right? And so the numerator being zero is going to point out maxima and minima. Now, we got some other interesting things going on in this picture, because if I'm drawing this graph along here, the slope right here, let me make it less vertical. The slope here, going along this way, when I said we can monitor motion, is going to have a slope like this at that t. And whatever t gives me all the way around here is going to have a slope like this. You understand? In other words, I'm going along the curve by changing the t. And at each point on the curve, I can figure out what the tangent line is. But because the curve crosses itself, later I may have a different tangent line. It's the same point, but I'm drawing it differently. This is a much more general way of talking about curves than is just a thing like you've had up to now. So, okay. So where does the book, what's the book do? The book doesn't do anything with functions, unfortunately. The book plays with symbols. The book uses dy, dx, and to do this problem right here, I should say dy dt, sorry. He does dy dx and dx dt. This is what the book, how the book presents it. And presenting it like you got dy dt, just make a fraction where you keep these things straight because they cross out. This is the way you do it. You may say chain rule, but this, if you look at this thing, I'm going to underline it. This is exactly the same as this thing. Because instead of y prime of t, you can write dy dt, right? If x is x of t, then dx by dt is what I would call x prime of t. This is bad notation, but that's, we use this notation for derivative. So this says a derivative of y with respect to t. This says a derivative of x with respect to t. That's right there. And this says a derivative of, I said phi. He says y with respect to x. Well, that's because x of t is x. But this does not show you that we have a composition here. This notation doesn't show you. Now, what I want to do is ask you guys, see who's smart enough. What if I want to differentiate twice? How do you differentiate this twice? With respect to t? Well, okay, you do d dt of dy, dx, dx, dt. Product. So I do d dt of dy, dx, leave the other dx, dt alone, plus I do d dt of dx, dt. And so I'm just going crazy here. I'm going to have a lot of fun. This is d dt of dy dx times dx dt plus d dx, everybody knows that's d2, x by dt2. That's the second derivative. This one makes sense. That's the second derivative. My question to you guys is, what is this? I am not smart enough to figure that out unless somebody tells me what the answer is and I memorize it, and then later I go just in my memory, I recall it and I write it down. I'm always right. And everybody thinks I know what I'm talking about. In my opinion, this is hard to understand. Okay, so let me try to show you what happens if we do it this way. Okay, now what I'm hoping you'll see here is all of this makes sense, but this is kind of complicated. So I'm going to call it h of t. I'm just going to name it something because I'm trying to understand. So I don't understand it. I'm going to name it something. So I have h of t is phi prime of x of t. Now, I'm hoping that it will click on you guys. I'm going to put boxes around two things, and I want to look at the two box things, thing at the top here and down here. What I hope you see is this up here is y is phi of x. This down here is h is phi prime of x. If you stare at these two things, you should see it's the same kind of thing. On the left, we have a function. On the right, we have a composition of functions. Up here, it's phi of x of t. Down here is phi prime of x of t. That's just still the composition of functions. Now, we didn't have any trouble differentiating this one because we used the chain rule. So you shouldn't have any trouble differentiating this one. You use the chain rule. So the derivative of h is the second derivative of phi, with this leaving x alone, times the derivative of x. Now, again, if x prime of t is not 0, see here it appears again right there. What I can do, my space is the problem as usual. The second derivative of phi at x of t is equal to the derivative of h divided by the derivative of x. Now, I contend this is easy to understand because all I did was do the chain rule again. Now, over here, you have to do the chain rule on this thing. It just doesn't look like a chain rule. Okay? And so, in any event, the point here is, what does the second derivative of a function tell you? It tells you about concavity. Concave up and concave down, remember? So I can find out what's happening to my curve. It's 22 after. I find out what's happening to my curve by differentiating the answer, the function I came up with, differentiate that with respect to t, and divide by the derivative of the x function with respect to t, and the result of that will give you the curvature. So we can study the curve, we can find out where it's increasing and decreasing, because that's this formula here, wherever I wrote it, right here. The derivative is positive if both of those are positive or both of those are negative. We can find out where the curve is going up, where it's going down, and using this formula, we can find out where the curve is curved up and where it's curved down. So this formula I recommend to you and this formula I recommend to you. This to me is harder to understand. Okay, so time is over in the sense of the class. I've got to stop recording.